So we are recording now. Hello, everybody. Hope everybody's doing well and that you've had a chance to take a look at video number 4 and video number 5, which are the ones that are cover the beginning of chapter 7 and the SN2 reaction, which is the second reaction that's on your worksheet here. You will see why we started with SN2. As we move through the chapter, you will see that it makes sense to start with SN2. And then move on to SN1 and then do the other ones. So I was wondering if anybody had any burning questions to start with, any part of the chapter that you would like us to jump in. I'll wait for you to tell me. What were the hardest things to understand from those videos? What was the trickiest part? Shelby, I do see your question about the homework, and we will get to that one, I promise you. I'm going to wait to see if there are any questions. And if not, I'll go ahead and share my overheads with you, and then we can briefly talk about what's posted on the overheads. And then we'll do the homework, I promise. Well, talk about the homework. No questions yet. Okay, well, let me go ahead and share my screen. And we'll talk about what's posted on the overheads. And remember that you can ask questions or interrupt. This is not a one-way thing. This is just a help session, okay? So first thing that I wanted to remind you guys is that this chapter is mostly about alkyl halides. So we need to be able to name those. And for some reason, in the time that has passed between when we learned the names of the halides to now, a lot of people have forgotten them. So if you have a bromine substituent, we call that bromo. You'll remember that, right? If we have a chlorine substituent, we will call that chloro. And the most important thing for you to remember is that those chlorine or bromine or fluorine substituents, they're not more important or less important than the alkyl substituents. They have the same amount of importance when you're naming, okay? So if you're writing the name of something like this, there's a bromine here, but there's also a couple methyl groups. Your job is to make sure that everybody in there gets the lowest possible numbers, okay? Because there is a bromine, that doesn't mean you're going to start numbering in this direction. You're still going to give everybody the same importance. Now, in a situation like this one, where the bromine is closest to the end of the chain, you will start numbering here, and that will give bromine the number 2, and the methyl groups will have higher numbers. So the main thing that I always feel like I have to remind my students of is just because this chapter is called alkyl halides and because you have halogens in the name, that doesn't magically make the halogens more important than the alkyl groups, okay? You still name so that everybody gets the lowest possible numbers. You guys didn't have any trouble with the naming part, did you? Anybody? No? Okay. Now, this is a good time to talk about what happens if you have two alkyl halides that are at the same distance from the end of a chain, okay? Two halides or a halide and an alkyl group. So here is our parent chain. It's a hexane chain. It has a bromine attached to it, and it has a methyl attached to it. And as you can see, the bromine is on the second carbon from the end, and the methyl on this side is on the second carbon from the end. We made a decision on where to start numbering that chain by using alphabetical order, okay? So bromo, B, comes before methyl, which is an M. So we start numbering this way. Does that make sense? Can I get some thumbs up or something? Thank you guys. It's really hard to tell if you're reaching people or not in this medium. So any help you can give me, I appreciate it. Thank you, Carrie. I do see your thumbs up, loud and clear. Okay, so those are reminders about how to name the alkyl halides, okay? Same importance as methyl, ethyl, propyl, no difference. Just make sure that you follow alphabetical order. So I think that we can jump into the SN2 reaction because that's probably where most of your concerns might be, even though I think Lanisha did a very good job explaining the SN2 reaction. There's still some things that we can discuss and we can probably clarify. So the first thing that you need to know about the SN2 reaction, which you can see here in the mechanism, but we can talk about it more than once, is that in the SN2 reaction, your nucleophile, which is this species that has a negative charge or a negative character, has to come from the back of the molecule, okay? Have you guys spent any time thinking about that part? Okay, so let's see if we can do a little drawing here. Let me change this view to the document camera. Hopefully this will work. Give me just a second. There we go. That is not working as well as I expected it to. Says that it's not responding. Okay, well, we'll go back to our video. That's definitely not letting me share anything with you guys. Sorry about that, guys. I don't even know if you can hear me right now.
I can hear you. You're just frozen on the screen.
Okay, well, at least we can talk while we wait for this conflict to resolve itself. So basically, what I want you to think about is when we do an SN2 reaction, it's going to be very important that we realize that the only way this reaction can happen is if we have, I think that should have resolved the problem. There we go. The only way that this reaction can happen is if we can have our nucleophile come and attack the carbon that has the leaving group from the back, okay? So if we go back to the overheads, which are working, thank goodness, you will see that, can you guys see my overheads on screen now? You can? Thank you. You will see that your nucleophile has to come from the back, and then it can kick out the leaving group out of this side. Have you guys watched the video enough to understand what a leaving group is and why leaving groups are so important in this reaction? I see some heads going like this, which leads me to believe that not exactly. Okay, so let's talk about that. The SN2 reaction is a substitution reaction, okay? It's a substitution reaction, meaning somebody has to come in and substitute somebody else who's gonna go out, okay? That's what we call them, substitution reactions. If you're going to have a substitution reaction, you need to have somebody that is willing to leave your molecule so that the substitution can be completed. The part of the molecule that leaves is what we call the leaving group. And the leaving group has to be willing to leave. If the leaving group is not willing to leave, we're never going to accomplish anything. There's such a thing as good leaving groups, and there's such a thing as bad leaving groups. And I know that Lanisha in the video covered what makes a good leaving group and what makes a bad leaving group. So do you guys have any ideas on what could make a leaving group be considered a good leaving group? I'll take anything. I'm that.
It's based on the reactivity, right?
Well, the reactivity of the leaving group, what we're looking for here is ability to leave, okay? A good leaving group is a group that is willing to leave. If it's not willing to leave, we're not going to consider it good. So it really has a lot to do with the electronegativity of that atom. A very electronegative atom is not going to make a very good leaving group. okay? So in this example that I'm showing you here, your living group is this bromine that is here in pink, okay? Bromine is what we generally consider to be a good living group. Why is it a good living group? It's not very electronegative, and it's nice and big, and it can support a negative charge and leave with a negative charge to the bromine down here after it already left. It has to be comfortable living, and it has to be comfortable living with a negative charge. That's what we call a good living group, okay? If we were going to make a list of living groups and we were going to rank them, which has been done for you in an overhead that comes later, but we can take a look at it now since we're talking about it. These are the living groups that we're going to use in this class in order of reactivity, okay? Don't worry about this guy. We're not going to cover this guy over here. The main things that you need to think about are the halogens, which are going to be our favorite living groups. The closer they are to this pink side of the arrow, the better they're going to be, the more willing to live they're going to be. See where fluorine is over here? Fluorine, very electronegative, strong negative charge. Fluorine is not going to be very willing to live. Chlorine is going to be better. Bromine is going to be better. Iodine is going to be even better. Okay? Got that? Why is this important? Because somebody may ask you a question where they give you two reactions and they ask you which one of these reactions is going to happen faster or easier. And one of the things that you can look for is which one has the better living group. Okay? So those are typical exam questions that go with the SN2 reaction. Got that? Okay. So back to our SN2 mechanism, which was over here. You also need to have a good nucleophile, and a good nucleophile is somebody who has a negative charge or a negative character and is willing to come in and push your living group out. In the SN2 reaction, the two things happen at the same time in what is called a conservative process. The nucleophile, which is the blue guy, comes in, and the living group, which is the pink guy, goes out. And for a very, very short amount of time, you have this transition state right here. Did you guys get a chance to look at the transition state? What do you see in that transition state that kind of looks weird to you? Because this is not something we've seen before, right? What's going on here that is weird about this transition state? How many bonds is that carbon making in that transition state?
5.
It looks like it's making 5 bonds. Is that normal? Does carbon ever make 5 bonds? No, that is not normal. And the reason why we justify that in our heads is that both this bond with the incoming nucleophile and this bond with the living group are only partial bonds, okay? This one is forming, this one is breaking at the same time. And that's how we justify the existence of this weird transition state that has 5 things attached to the same carbon.
When you say justify, do you mean like we don't actually know that and we're just like making up a reason?
That's right. We're just making up our best guess as to what might be happening here. Nobody has ever seen this transition state. You cannot isolate this transition state. It actually, if it does exist, it exists for such a short fraction of time that nobody has ever seen it.
Mm-hmm.
This is only our best approximation of what must be happening when you go from here to here, okay?
Gotcha.
The difference with an intermediate, which we have seen in other mechanisms, is that an intermediate has a longer lifespan, and you can actually detect an intermediate, you know, like a carbocation. You can detect the formation of a carbocation. This guy here, you cannot detect. I mean, you can detect that something happened, but you can't isolate this guy, okay? So that's where the word transition state comes from. So what is the main thing that happened? Just describe for me, somebody with words, what happened between the top here and the bottom here. What was the transformation that happened there? What's going on in the top that is different than the bottom?
It switched from S to R.
Say that a little louder, Mason.
Oh, it switched from S to R.
It switch from S to R, which is the most important characteristic of this reaction, okay? In the SN2 reaction, if you start with S, you're gonna end up with R. And if you start with R, you're gonna end up with S every time. That's called inversion of the configuration, okay?
What do the S and R stand for?
S and R came from chapter 6. S means that if you were to rank the substituents around this carbon and do all the process that we learned in chapter 6, your substituents would be in clockwise order. I'm sorry, S means counterclockwise order. And in this case down here, if you rank all of those substituents and made a little model and put it with the hydrogen away from you, they would be ranked in clockwise order. That's what it means. R means your substituents are clockwise. S means your substituents are counterclockwise. Is that, I don't know who asked that, but is that clear? Sia, was that your question? Well, we're gonna
Sorry, you kind of broke up.
Sorry, say that again.
Yeah, that makes sense. You broke up for a second, so I didn't hear what you said at the very end, but thank you.
Okay, so one more time. In S, if you rank the substituents around the central carbon and you build a model and you turn it so that the hydrogen is facing away from you, your substituents are in a counterclockwise order. If you have an R molecule, if you make a model, rank your substituents, put it with the hydrogen away from you, the substituents are going to be going in clockwise order. That's in the short video that we had for chapter 6, if you need to take another look at that, okay? Okay, so we went from S to R, and in this case, we had bromine attached to our central carbon, and in this case down here, the bromine has been substituted by this OH right here. See that? That's what we call it, a substitution reaction. That's what the S means. The N means that it's nucleophilic. So we have a nucleophile that is in charge of doing the attack. And the 2 means that in the transition state, we have 2 molecules involved. We have the nucleophile involved, and we have this guy who is the reactant involved. We also sometimes call this either the starting material or the substrate. Okay, so those are all words that we can use to describe the material that we start with. So we went from this bromobutane up here, which was S, to this butanol down here, which was R. We got that transformation? Okay. So we talked a little bit about the transition state. What I would like to focus on right now is this stuff about steric effects. So steric effects is a fancy word that we use to mean how crowded with carbons is the reactive site, okay? That's what that word means. You guys ever heard the word steric effects before? I think this is our first time, right? Steric just means how crowded is your reaction site. Why is that important? In this mechanism, we have to attack the carbon that has the leaving group from the back, okay? So this is where we are going to do our attack. This is supposed to be a space filling model of this molecule here. So let's visualize that. This is carbon. This is the carbon right here in the middle. Can you all see it? And then this little white balls are hydrogens, which are very small and very close to the carbon, right? 1, 2, and 3 hydrogens, you see them? And then this big bromine here is this big red bromine here on the front. So if you were going to attack this molecule from the back, which is the way that the SN2 reaction works, it's also called the backside attack reaction. If you want to have a little laugh, let's have the laugh right now so we can move on, okay? If you were to attack the backside of this molecule, do you think that that would be hard or easy to get to this carbon? What does it look like to you?
Easy.
Easy, right? That carbon is completely unprotected. That carbon is very easy to approach. So it's very easy to do an SN2 reaction on a carbon like this one, on a methyl carbon. See how it has only hydrogens attached to it? That is the best possible substrate for the SN2 reaction, okay? On B, something has changed. What is different between A and B? You guys want to tell me what the difference is? Anybody?
Your methyl group, you have an additional methyl group.
There's an additional methyl group here, right? So one of these hydrogens has been replaced with this methyl group. Now this methyl group is kind of big and bulky. Can you see it up there? It's taking up a lot of room, isn't it? So if you were going to attack the backside of this molecule, would that be easier or harder than attacking the backside of this molecule here?
Harder.
But it's easier, A or B?
A is easier.
A would be easier to attack, right? Because it's easier to get to this carbon back here as opposed to this carbon back here. Is everybody okay with that? How about C? We have two methyl groups. Wow, the reactive side is getting crowded. Can you see how crowded? Do you think it's going to be easy to get to this carbon here in the middle or hard?
Hard.
It's going to be really hard. It's going to be so hard that most of the time this reaction is actually not going to be able to occur. It's just too hard to get to the reactive side. And finally, what's going on with D? Who wants to explain what happens with D? What does that reactive side look like to you?
It's very crowded, so it's going to be a
It's
lot harder.
tremendously crowded. So do you think that a nucleophile could actually sneak in here and get this reaction done?
Probably not.
Probably not. And that's why we have substrates that are good for SN2 reactions and substrates that are better for other kinds of reactions that we're going to learn later, like the SN1 reaction. So if I ask you to rank these substituents in order of how easy it is to do an SN2 reaction on them, what would the order be? Which one is the one that's easiest to do an SN2 reaction on?
Methyl carbon.
A, right? This is the easiest one. And then the next one would be
B.
B, which is this primary carbon here. And then the next one would be C, which is a secondary carbon. And the hardest one would be D, which is a tertiary carbon. Everybody got that? So that is what allows you to find the order in which those different reactions are going to be happening. Some of them are going to be super easy to do, and some of them are going to be really challenging to do depending on how available that active site is going to be. Okay? So that's, so far we've covered a couple of things about this chapter that are all interesting, right? And I think if Shelley's still around, that might help us to answer question number 3 in the homework. So let's take a look at that question. Let me change screens so you can see this homework. Okay, are you seeing question 3 in the homework now? Okay, so we're going to have to combine, Shelby, I hope you can hear us. We're going to have to combine 2 of the things that we just learned in order to answer this question. We're going to have to combine what is the most accessible reactive carbon in here, and we're also going to have to combine which leaving group is better of the ones that we have here, okay? So let's examine our substrates that we have here. If you look at number 1, this is where the bromine is attached, right? This is the leaving group. This carbon, the one that I have my little arrow on, is the one that I need you to consider. Can you guys see that carbon? Okay. This carbon that is attached to the bromine, what kind of carbon is that? Is it primary, secondary, or tertiary? How many direct carbon neighbors does this carbon have?
Primary.
I didn't hear that. Can you guys say that louder?
Primary.
That
Just
is
one
a
carbon.
primary carbon because it only has one direct carbon neighbor, right? So this is a primary carbon. Is it hard or easy to do an SN2 reaction on a primary carbon?
It's relatively easy.
It's fairly easy, right? Definitely easier than secondary or tertiary. That's what we just learned. True? So let's look at number 2. Number 2 has the chlorine attached to this carbon right here. How many direct carbon neighbors does that carbon have?
2.
2, so that makes it secondary. Do you think that compound number 2 is going to react faster or slower in an SN2 reaction than compound number 1?
Slower.
Slower.
Slower, okay? So we know that 2 is slower than 1. Do you see where we're going with this? We're reasoning through them one at a time. Now, compound number 3 has the chlorine attached to this carbon right here. It's even hard to put a cursor on this carbon because it has so many carbon neighbors. How many carbon neighbors does this carbon have? The one that I'm sitting my cursor on?
3.
3.
3. So that makes it tertiary. And what did we just say about doing SN2 reactions on tertiary carbons?
Almost impossible.
Almost impossible, right? So of all the things that we've seen so far, this would definitely be the least reactive one towards an SN2 reaction. Shelby, is this making sense to you? Can you give us a thumbs up or some signal? I'm gonna hope that it is, because I haven't heard from Shelby.
She typed in yes into the chat.
Oh, she said, yeah. Okay, perfect. Thank you so much. And then the last one here, number 4. 4 looks a lot like 2, doesn't it? It looks a lot like 2. It has the leaving group attached to this carbon here, and that carbon is what we call what? Primary, secondary, or tertiary?
Secondary.
That's a secondary carbon. So here's what we know so far. Number 3 has a tertiary carbon, so it definitely has to be the slowest one to react, okay? So we're gonna put number 3 at the very front of our answer because it says to start with the least reactive, okay? So number 3, least reactive of them all. Number 1 has a primary carbon, so we know that number 1 is going to be the most reactive. So number 1 needs to be at the very end of our answer. So far, it looks like answer B is shaping up to be the most promising one because it has 3 in the beginning and 1 in the end. Now, if you're wondering between 2 and 4, how do we rank 2 and 4 if they're both secondary carbons? What could we use to rank those two guys?
The leaving group.
The leaving group. And who's a better leaving group, bromine or chlorine?
Bromine.
Bromine, because it's bigger and less electronegative, right? So if bromine is more willing to leave, that means that this guy is going to be slower than this guy in a reaction that is SN2. Does that make sense?
Yeah. So whenever doing a problem like this, go from looking at the carbons first and then to the leaving group.
Yes.
Okay.
First, you rank the carbons based on whether they're primary, secondary, or tertiary. Or
Okay.
methyl, you could have a methyl carbon, which would be extra fast, right?
Mm-hmm.
And then if you have 2 that are both secondary or both primary, you look at the leaving group and you rank based on the leaving group.
Thank
Okay? So the correct answer would be B, because it means that the slowest one is number 3, the second slowest one is number 2, then 4, and then 1 is the fastest one. Okay? So that's how we would answer that question. So I want to do a little bit of work on filling up our worksheet. Okay? I'm going to stop sharing the screen so I can see the chat. Okay. And I hope I'm not frozen anymore. And Shelby said that she did get that, so that's great. Are there any other pressing questions before we start to fill our worksheet here?
I actually had a question about WebAssign
Mm-hmm.
for the lab 5.
Yeah.
I wasn't really understanding what for the pre-lab, what the second question is asking, like how it's set up. Like I don't understand what it's trying to get at.
Okay, I don't have WebAssign open, but I'll go ahead and open it while you guys think of other questions, okay? In fact, Carrie, let's get going with our worksheet, and then at the end, we can answer lab questions so that we can leave them for the
Gotcha.
end, so people don't have to sort through them. So, how are we gonna fill this worksheet? The first thing that it says there is, show me the SN2 reaction, right? Show me an example of the SN2 reaction. They're not asking you for the mechanism, they just want an example of that reaction. So what do you guys want to use as your example of an SN2 reaction? Would be my question to you. Because the one that we have in the overheads as our first one is the mechanism, and the mechanism is kind of complex. So I would like to start with a very simple one that we just use as an example. Has anybody found an example that they like for this reaction?
We could do 1-bromobutane.
From the lab, just from the lab.
Yeah.
Okay, let's do that one. Since my document camera doesn't want to work, I'm going to do that on the whiteboard. So you're going to have to bear with me because my drawing skills on the whiteboard kind of suck. But Carrie has requested that we do 1-bromobutane because she's really worried about the lab. So let's do that. So 1-bromobutane.
I didn't see it.
Can you see what I'm drawing here? I told you that my drawing skills on the whiteboard are terrible. But would that be considered to be 1-bromobutane? We have 1, 2, 3, and 4 carbons, and we have a bromine on carbon 1, right? Now, we're doing the reaction right now. We're not doing the mechanism. So there's going to be no curvy arrows here. We will do that later. What do we want to add as our nucleophile to 1-bromobutane? And I'm going to read Carrie's mind, and I'm going to assume she wants to use sodium iodide. Is that true? Yeah. See, I'm getting really good at this mind reading stuff. Okay, so we're going to use sodium iodine. Sorry again for my poor drawing skills. This is an I. Let me make it better. I just can't stand it. Sodium iodine is going to be our reagent. There we go. And now we're just going to draw the product of this reaction without explaining what the whole mechanism was. We will get to the mechanism, I promise. But right now, we're just showing the reaction. What will happen to this carbon chain over here? Will anything change within the carbon chain?
No.
No. So can I copy it to the other side? Yes, I can, right? And this bromine is going to get substituted for this iodine here. So now I'm going to have iodo-butane. And where does the bromine go? It will combine with the sodium, right? So now I'm going to have sodium bromide. Oof, that B was really iffy. As my product, okay? So that is the overall reaction for the SN2 reaction. This is SN2. And this is just the overall reaction. We didn't do the mechanism. We just showed what happened, generally speaking, and going from one side to the other, okay? So some words that might be useful here. This guy, the guy that the reaction happens to, is what we call a substrate. So I can put a text box here, which is gonna look much better. So that's what we call the substrate. Another name for the substrate is the start or starting material. Okay? This guy here is what we call the substrate or the starting material. This guy over here is going to be our nucleophile. The iodine is going to be our nucleophile. And iodine is considered to be the nucleophile when we had a negative charge on it. But you can't go to the store and buy a bottle that has only I- in it. You have to buy it as a complete chemical, okay? And the chemicals that we're gonna use in this particular reaction always come, like this one, with either sodium or potassium attached to them, okay? So our nucleophile is gonna come in the form of a salt. Salt means that you have either sodium or potassium attached to it. Okay, so those are popular nucleophiles. Now on this side here, this guy, let's move it over here. This guy is what we will call the product, okay? And this sodium bromide that we have here is also a product of the reaction, but it's not the organic product, so it's not the most important thing, okay? We need it to complete the reaction, but this is the organic product which I am going to be looking for. So can we put this reaction in the box that's on your overheads that says SN2 reaction? So that would be that first box over here. Does that make sense? Yep, that's where that reaction would go. Now, you have a box here in the middle for your mechanism for the SN2 reaction. Everything is backwards on Zoom. Here we go. So in that box, you can copy the mechanism that's on the overheads. You can copy the mechanism that's on the video that Linisha made. It's the same one, okay? The important thing about that mechanism is that it has to show that transition state, okay? Transition state that has the 5 things that look like they're bound to carbon at the same time. So this guy here is your reaction for SN2, and the mechanism for SN2 is the one that you can find in the overheads. Everybody following along with that? So we have our reaction, we have our mechanism. Thank you, Caitlin, for the thumbs up. The next thing that we're going to be looking for is what to put in that box that has the notes. So the notes box is supposed to be the part where you put important information that can help you decide whether you should use this reaction or not. For example, in your notes box, you could say, what is the best kind of substrate to do this reaction in? And what is the worst kind of substrate, okay? So what do you guys think would be the best kind of substrate for this reaction? Let's make, let's clear this up and start over with best substrate. And then here on the bottom, we're gonna put our worst substrate. So what kind of carbon would be the best substrate for this reaction? Primary, secondary, or tertiary?
Primary.
There's one that's actually even better than a primary, which is the methyl carbon, right? Methyl is the absolute best. And then the next one is going to be primary. And then after that, we're going to have secondary. And what is the absolute worst substrate that we could have for this reaction? Tertiary, right? I feel like I'm working extra hard today to read your minds, guys. So methyl is the best substrate. Primary, still good. Secondary, we can do it, but it's going to be tight. And tertiary, we better not try to do this reaction on a tertiary substrate. Okay? This is something that can go in the notes section as where's your best substrate and what is your worst substrate. Can we add that to our notes section? And then the last thing that I want to add to our notes section, I'm going to put a line here in the middle so we all know that we're talking about different things. This is one more thing, okay? This also can go in your notes. Is what is your nucleophile going to look like here, and what are the best nucleophiles you can use for this reaction, okay? So one of my favorite nucleophiles for this reaction is sodium iodine, like you used in the lab, Carrie. That is an excellent nucleophile to be used in this reaction. If you don't have sodium iodine, you can also use potassium iodine. They both work equally well, okay? So those are nucleophiles that you could use. You could also use something like sodium bromide or potassium bromide, okay? Those will work as well. Sodium chloride is a nucleophile that you could use. Not as good, but it will still work, okay? You can still use that as a nucleophile for this reaction. There's a nucleophile that was used in the mechanism that Linisha showed you, and that's in the overheads. And that one is sodium hydroxide, okay? You can also use potassium hydroxide. Either one of those would work. You have to be very careful with these two nucleophiles because you can get a competing elimination reaction.
For the NaCl, did you mean to put KCl on the second column?
I did. Thank you for telling me. Let me fix that right now.
One other thing, Christine asked, does the best versus worst substrate only work for SN2?
There's going to be a best to worst substrate for SN1 as well. And here's a spoiler alert. The order of the substrates is going to get reversed when you get to SN1, okay? So the worst substrate for an SN2 reaction is going to be the best substrate for an SN1. I hope that answered Christine's question.
Hey there, yes it did. I had already put the reactivity of substrates on the back of my worksheet, and so I just wrote down that this is for SN2 only.
Yes, this is for SN2 only, and when we get to SN1, it's going to be the exact opposite, which is nice because if you learn the SN2 order, you can just reverse it for SN1.
Awesome,
Okay.
thank you.
Okay, so what do you guys see in common about all these nucleophiles? What do they look like to you? Either sodium salts or potassium salts, right? They all come in the form of a salt, and that's because when you're doing an SN2 reaction, you're going to usually use these kinds of nucleophiles that are very effective in delivering the nucleophile to the active site, okay? Another nucleophile that you can use is called sodium cyanide or potassium cyanide. Both sodium and potassium can be used in this reaction. It doesn't matter which one you use. Sodium cyanide and potassium cyanide are also very good nucleophiles for this reaction. We don't like to use them in real life because they're poisonous, but since we're fully online and only online, there's no chance of you getting poisoned, so we can use them here, okay? See all the nucleophiles that you can use in this reaction? Okay, so these are our nucleophiles. So let me move this out of the way. There we go. So these are nucleophiles for SN2. And as preparation for our next session, the nucleophiles for SN1 are going to be different. Okay, they're not going to look like this. If somebody gives you one of these nucleophiles, they're trying to tell you that you're going to do an SN2 reaction. That should be a clue for you. There's also a couple solvents that are good for SN2, so we're going to put them here. And remember, the solvent doesn't take part in the reaction, but it can give you a clue of what kind of reaction you're trying to do. And those solvents are acetone. Acetone is the most common solvent that you will see for the SN2 reaction. And there's one more that you've never seen before, unless you have horses or cattle, then you've seen it before. And that solvent is called DMSO. DMSO stands for dimethyl sulfoxide. DMSO is a very, very stinky solvent that is used in veterinary medicine a lot. And it's also used as a solvent for the SN2 reaction. So if somebody tells you that you're going to use one of these nucleophiles and that you're going to use one of these solvents, what they're trying to tell you in that question is think about the SN2 reaction, because it's very likely that you will be using, if you're using this kind of nucleophile and this kind of solvent, it's very likely that that's going to be an SN2 reaction. We got that? Did we get all those notes typed up? I mean, copied, whatever, into your worksheet? Okay, I'm gonna stop sharing for a second so I can see what's in the chat. Okay, everything looks good. And does anybody have any pending questions about the SN2 reaction that we haven't covered, or about anything else that's going on with the class that we haven't covered?
I just have a quick question about one of the labs, but we can do that afterwards if there are other questions.
Let's see if anybody else has a class question, and then we'll take the lab questions in order, okay? Any other class questions, guys?
Yes, ma'am. What do we need So I know we have one homework that's due this afternoon, but what is due for Thursday? Have you posted that yet?
No, I'm gonna post that this afternoon. I always wait until we close one homework to post another one so that we don't get overwhelmed with homework.
Okay, awesome. Thank you.
And remember, Christine, that if at any time you need an extension, because I know that Tuesday to Thursday frame is really tight, you just need to let me know. Okay, that's not a problem.
Okay, thank you. I appreciate that.
And that goes for anybody in the class. If you need an extension, you just let me know. That's not a problem at all. I mean, I do appreciate the work that you're putting in, and I know it's hard. It's hard for me, and I'm the one writing the homeworks. I can only imagine how hard it is for you. So you just let me know. Other questions? Should we move on to lab questions? Okay, Carrie, this is your moment to shine. What is your lab question? You said it was from WebAssign and it was question number 2. Can you read it to me?
It says predict the outcome of each set of experiments, justify your prediction. Part 1, effective structure. And then it says 1 bromobutane, 2 bromobutane. And then the options is will react first, will react last, will not react at all. So I just don't understand what the actual question is.
Okay, so that question is very similar to the homework question that we just did, right? Draw 1 bromobutane and actually, let's do it together. Let's put it on the whiteboard and we can do that together so we can address that. Let me clear this. So for part 1 is effect of the structure, right? So you have 1 bromobutane, which looks like this, more or less. And you have 2 bromobutane, is that what you said?
Yeah.
Do you agree with me that that's more or less what 2 bromobutane would look like in the worst planet drawing in the world?
Looks good.
Okay, so what do we know about this reaction that may help you predict which one of them is going to react first?
Looking
Which one
at
of them is going to go faster?
1 bromobutane.
So we do know that this guy here, oops, let's undo that. That's not what I wanted to do. Let's draw a little circle around the reactive carbon. This is the carbon that has the leaving group, right?
Yeah.
In that case, and in this case down here, this is the carbon that has the leaving group. Of those 2 carbons that we have circled here, how many carbon neighbors does this one have?
1.
1, so that's what we call a primary carbon, right?
Mm-hmm.
And how many carbon neighbors does this one have?
2.
2, so that's what we call a secondary carbon.
Yeah.
Lab number 5 is all about the SN2 reaction. So which one of these guys would react faster in an SN2 reaction? 1 or 2?
1.
Definitely 1, okay?
Okay.
And I think that there is another prediction that you have to make that has to do with the leaving group, right?
Yeah, there's 2 more. It's the leaving group and then the steric effects.
And in the steric effects, notice that in one of them, they're giving you a really big and bulky neighbor.
Uh-huh.
Consider how hard it would be to get to the reactive carbon when you're answering that question.
Okay.
Remember the picture that we did with the space filling models?
Yeah.
If you had a really big bulky neighbor, that would make it harder to get to that reactive side.
Mm-hmm.
Okay?
Yeah, I wasn't sure if we were like comparing them to each other or like.
Yes, you're
Like a-
comparing them to one another.
Gotcha.
Like we just did here in this order.
All right. Thank
Okay.
you.
You're welcome. And Sia, you said you had a lab question too? Sia, you're muted. I can't hear you.
Sorry about that.
That's okay.
I just had a problem with the measurements. I kind of just wanted to make sure I got them right because I printed out this sheet.
Uh-huh.
I don't know. I'm just kind of paranoid about the
Did you
measurements.
watch the video that I sent you that tells you
I
how to do
did.
the measurements?
I did, but like they had something for the width like 17 millimeters, and I'm just confused because for ours it didn't look super different, but I had like 3 millimeters with my ruler.
17 millimeters was the measurement in the one that's posted on WebAssign because that was a super wide peak, right? Your
Yeah.
peaks are narrow, and I do think that the width and half height is about 3 millimeters.
Okay, so
That-
I just didn't know like for exact measurements because my ruler is like just one from a regular kit.
You know, that's gonna, what was the proportion that you got when you calculated those percentages? Was it close to 80-20, even in the neighborhood of 80-20?
Yeah.
Yeah, that's what we're looking for.
Okay, I just want to make sure because I didn't want to get it.
Yeah, the learning objective for that lab, Zia, is that you understand that each one of those peaks can be approximated to a triangle, right?
Mhm.
And if that we had a really good ruler, we could have really good measurements, but you just have a ruler like I do in my kitchen, which is not
Yeah.
the most accurate, and you're still getting the same percentage as the rest of the class is getting. So that's good. You're doing good.
Thank
And
you.
for anybody else that didn't understand the question that Zia was asking, because she and I had some back talk via email, she's asking about measuring the peaks for lab 4, okay? And all you have to do is get that picture that is linked from the VR website, either print it or put it on your computer screen and measure it with a ruler. It's not gonna be the most accurate measure you've ever done, but it's gonna be good enough to get the percentages. Okay? Any other questions? I see that some people are starting to leave us, so that's probably meaning that we have exhausted all the questions that we had. Does anybody else have anything good to share that we should know about? No? I was able to make a lemon meringue pie and it turned out really good, so I'm very proud of myself. I'll send you my, oh, I see Zia's cat. What's your cat's name?
It's my roommate's cat. Her name is Winnie.
What's her name?
Winnie.
Oh, she's so cute.
Yeah, she's so cute.
She wants to learn organic chemistry. Welcome, little cat. Anybody else doing anything fun or interesting? No? Are we struggling? No? Okay, well, at least we're not struggling too hard. Well, guys, if there's not any more questions, I'm gonna stop the recording because we don't want to just fill people's emails with nothing. So let me stop that.